Okay, intermolecular forces. Now, the reason we've been doing the reason we did dot and cross diagrams, kind of, not the reason, but it led us into Vesper diagrams. And then the Vesper diagrams led us into polarity, right? And now the polarity is going to help us into intermolecular forces. And intermolecular forces are so important, okay? They are the things that identify what a substance boiling point will be. So every substance has a unique boiling point. Water boils at 100 degrees Celsius. Exactly 100.00 degrees Celsius. And nothing else boils at 100. So if you have an unknown, clear, colorless liquid, and it boils at 100, that must be water. This is how they know if they find water on Mars. They take this clear, colorless liquid, and they boil it, or they find out what its boiling point is. If it's 100, it's water. This is how scientists find out what they've made in their little flasks that have lots of chemicals inside. If they take a section of it and they look at its boiling point, they can see exactly, or its melting point, it's the same conversation, the melting point is also unique. So if they've made a solid, they can melt that and they can go, we've made copper. This is definitely copper. Because you know how many like silver metals there are, right? So if you've just made a silver metal, if you take a flake of that and you melt it, you can then tell if that silver metal is indeed silver or chrome or titanium or whatever, because each one has a unique melting point. That goes for liquids and solution, not solutions, but every pure substance. Does that make sense? So the reason it has these is because they all have unique intermolecular forces. Now, intermolecular, when we talk about intermolecular, although I was using metals as my example there because it's easy for us to understand that lots of metals look the same and that therefore they'll have different melting points, which is still true. When I'm talking about intermolecular compounds, I want to talk just about molecules. What's a molecule? This whole package. What's a molecule? Two nonmetals that are stuck together how? Covalently bonded. So as soon as I'm talking about an ionic compound, you cannot talk about intermolecular forces. Does everybody get that? Okay, so when you're talking about intermolecular forces, you better be stuck in that category in your head, in that file in your head, that's only about molecules. So we're talking about methane and ammonia and methanol and, right? Everything we've done Vesper diagrams on, we can be here for this. As soon as you're talking about sodium chloride, oh, no longer are we talking about this anymore. Okay? If we're talking about sodium chloride's boiling point, we're talking about those ionic bonds. Do you remember? And the property, the fact that they're in a lattice structure, and then we'd have to break all that lattice structure down for it to melt and boil. Do you remember us talking about that, about the molecule? Aha. So that's that conversation. We've already had that conversation. If I'm talking about the melting of a metal, I would be talking about the rows of cations and having to pull those cations apart from each other to move those circles, because remember, solid, right, liquid, do you remember this? Yeah. And gas. So in order to melt something, you have to take these circles and move them apart. In order to boil something, you have to move them apart even further. So what are these circles? Well, in an ionic compound, that's that big crystal lattice structure. Remember? The rows of cations, like each cation is surrounded by 6, for sodium chloride, 6, right? Yeah. For a metal, we're talking about those rows of cations, delocalized electrons. But here, in the molecule, we're talking about intermolecular forces. So it's really important you go back to your Science 10 and kind of go, is this ionic? Is it an element? Is it, right? So that you know which conversation to have when I'm talking about boiling point. Okay, so intermolecular forces, covalently bonded two nonmetals. Inter, as in like an international event, or an internet, means between And so forces. So we have a force that's between two molecules. Okay? A force that's between two different molecules. So I just erased the solid, liquid, gas because I'm going to draw it a bit bigger. Let's take ice. So it's a solid, right? And inside my rows and columns of ice, I have an H2O. And it is V-shaped. And I can draw it in both a Vesper diagram or a dot and cross diagram because I am a smart Chem 20 student. Everybody get that? And if I am melting ice, it's still H2O, right? So all I'm doing when I'm melting ice is taking a liquid and moving these further apart. They're still supposed to be touching, but I kind of want to make a point. Move them apart from each other. But it's still H2O. Get it? I am not breaking those sticks. If I break that stick, it's called a chemical reaction. It's not called boiling. And do you remember in, like, I don't know, Science 10 or junior high or something, you learned about physical changes and chemical changes? And a physical change was melting it, and a chemical change is breaking that covalent bond. So we're going to talk about breaking these intermolecular forces. And when I talk about breaking intermolecular forces, I'm literally talking about moving these circles further apart from each other. But you will not believe how many students tell me, oh, you must be breaking that bond, that covalent bond. No, that's a chemical reaction. That's not boiling. So that whole like fundamental understanding of chemical change, physical change, it applies here. Breaking that covalent bond is a chemical change. I'm going to have to make water become hydrogen and oxygen or something like that. Right? I'm making it become sodium hydroxide. I'm just boiling it, actually. That's what intermolecular forces are about. It's just boiling. Okay? Or water vapor, and you have you have a H2O here and an H2O here. Okay, so what's the difference between a solid, liquid, or a gas? What makes it become a solid, liquid, or gas is the attraction between these particles in there. Okay? And these are called intermolecular forces. The forces that are holding in between these molecules and sticking them together. So the more intermolecular forces I have, the closer packed together it'll be. Can you see that this isn't going to have very many intermolecular forces? I've broken them, and therefore they're able to move far apart from each other. Did you get that? Okay, so there are three kinds of intermolecular forces. All right, three kinds of forces that stick these things together. The more forces, the more intermolecular forces you have, the higher the boiling point or melting point. Same thing. Not same thing, obviously, but same concept. Okay? Why? Well, if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 forces sticking these two balls together, okay, and I need to break those forces in order to pull those two molecules far apart from each other and let them become a gas. Do you see that? I have to break all 10. So break, 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 break. That's a lot of energy. Breaking, 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 breaking. A lot of energy, right? Where's that energy coming from? Well, my Bunsen burner or my stove to make that pot of water boil. Do you get it? So if I have to put a lot of energy in, that energy is temperature. If I have to put a lot of temperature in to make it to boil, it's going to have a high boiling point. Versus a different kind of molecule, which might only have one. Break it, gas. Well, that didn't take very much energy or temperature, and therefore the boiling point will be very high because it boiled right away. Does that make sense so far? Okay, so 3 kinds of intermolecular forces. 1, London dispersion forces. 2, dipole-dipole forces. And 3, hydrogen bonding. Okay, so what are London dispersion forces? London dispersion forces, which are also called van der Waals. And in fact, actually, do you see, in your note package, you've got that, right? That the London dispersion forces are called van der Waals. But accidentally, beside the dipole-dipole, we notice that it says van der Waals as well. No, those aren't van der Waals. You can scratch those out. Do you see that? In the title, intermolecular forces. 1, dipole-dipole. 2, hydrogen bonding. 3, that right here.
Yeah.
Got it? And then at the top here it says dipole-dipole forces, van der Waals forces. No, can you scratch that out? Because they're different. And in fact, actually, London dispersion forces and van der Waals are different as well. But in the Alberta curriculum, they seem to use them very interchangeably. And so the Alberta curriculum thinks that they're the same thing. So you're going to think that they're the same thing for now. But they aren't. They're slightly different. They are slightly different to each other. But we won't get into that. Okay? So, London dispersion forces, or van der Waals forces, are these water molecules. I'm going to draw just 2. I'm going to take this out so I can start writing. Between 2 water molecules, this is a shared pair of electrons. Everybody okay with that? They are, as we know, shared closer to the oxygen than they are the hydrogen, because the electronegativity difference is different and they pull towards the oxygen. Everybody okay with that? Okay. But these electrons are going to be attracted to the protons in these nucleuses because they're right beside each other. Do you remember when we were doing our metallic structure and I had Katie move her arms out and I said, okay, there's the valence electron, and oh look, it's right beside another nucleus. And so the electrons way out there are actually just as attracted to this nucleus as they are to that nucleus. Do you remember that? It's the same idea. These electrons, although they're not delocalized, so it's not like so much so that they can remove. These electrons are still committed to that bond. However, they're kind of glancing over there and going, actually, that's all right, I'm quite attracted to that, and that proton as well. Okay? So 2 magnets that are stuck close together, if I bring another magnet into the field, that force field and that force field do overlap. There is an attraction there, even if those magnets don't slide together and stick together. Does that make sense? Sort of? Okay. Do you need another analogy, or are you good? Okay. So these electrons are going to be attracted to these protons. And these electrons are going to be attracted to these protons. It's a 2-way street. There you have both of each other. Okay? So if you've got that attraction happening, they're going to stick together. So that's what these are. It's the electrons in one molecule being attracted to the neighboring molecule. Protons. Didn't finish. Why are all my pens so dull? Okay, so the electrons in one molecule, oh, I can't see it on the board there, electrons in one molecule being attracted to the neighboring molecules' protons. Everybody get that? Are you awake?
Yeah.
Good. Okay, so which molecules have London dispersion forces? Not a trick question. Easy answer.
When there's two compounds?
Right. When there are any compounds, 2 compounds, intermolecular forces, any compound has electrons. Yes? Any compound has protons, right? So every compound has intermolecular, or has London dispersion forces. I'm going to put that in blue. That make sense? All compounds have electrons, all compounds have protons, so all compounds have London dispersion forces. Okay? Okay. Dipole-dipole forces. What are dipole-dipole forces? Well, this water molecule of ours is polar, right everybody? And the end above the oxygen is relatively negative, and this zone down here is relatively positive. Does that statement not ring true for this one as well? So this zone up here is relatively negative, and that zone down there is relatively positive. What do you see has just happened?
Neutralize.
Not neutralize, attract. See that?
Yeah.
So the relatively negative end of this water molecule will be attracted to the relatively positive end of the other. And one beside, and one below, and one in front, and one behind. Because we're not talking about just two molecules. And so water literally arranges itself in these V-shaped stacks because of the dipole-dipole interaction. So this is called dipole-dipole. And the dipole-dipole interaction would be the
Junior class change.
negative end of one molecule being attracted to the positive end of the other molecule. Did you get that? And likewise. And so which molecules have dipole-dipole interactions then? Any molecule that is polar. Very good, Michael. Everybody okay so far? Okay, so the things that stick these circles together are called intermolecular forces. There are three kinds of intermolecular forces. One is London dispersion forces. It's saying that the protons in here will be attracted to the electrons in here, and the protons in here will be attracted to the electrons in there, and that sticks them together. Good. The next one is dipole-dipole. It's saying, hey, if these circles are polar, then the relatively negative end of that will be attracted to the relatively positive end of that. Oh, good. Okay, that's dipole-dipole. The third is an extreme dipole-dipole. Sometimes this polarity is so strong that it's almost ionic, and if it's almost ionic, then this is almost an extreme plus and an extreme minus. And then we get a special kind of attraction. We're going to call that a hydrogen bond, because it only happens in hydrogen. Because remember, hydrogen's weird, right? And hydrogen likes to become H+, and so, you know what, it's okay with being that extreme polar bond. So hydrogen bonds exist in HO, HF, and HN. HO is in like water, HF as in, well, hydrogen fluoride, and HN is in, for example, ammonia. And this is so super polar. I'm going to put like this and like this. That bond is so polar. It's uber polar, and therefore we've given it its own special name. So it has dipole-dipole and an additional uber polar charge called hydrogen bond. Okay? So if you think it has hydrogen bond and you've said it doesn't have dipole-dipole, there's something wrong here. Because if it has dipole-dipole, it might have hydrogen bonding, but if it has hydrogen bonding, it's definitely polar, because this is an uber polar bond. Does that make sense? Okay, so I did say the more intermolecular forces, the higher the boiling point. So let's look at, for example, water. Boiling point is 100 degrees Celsius, right? And let's look at methane. And I have no idea what methane's boiling point is. Let's talk about nitrogen then, because I do know nitrogen's is about minus 80 degrees Celsius. Okay? And of course nitrogen 3 bonding electrons. Looks like that. So, does water have, the question would be something like, explain why water's boiling point is so much higher than nitrogen's boiling point. Okay? And the answer is going to be this. Water's boiling point is higher because it must have more intermolecular forces. The more intermolecular forces, the higher the boiling point. So this must have more intermolecular forces. Do you understand? That's already the answer. However, of course, I'm going to ask you to explain your answer or prove your answer, or, right? So let's show its intermolecular forces. So the first thing you do is you just list them. Does water have London dispersion forces? Yes, because all have London dispersion forces, because all have electrons and protons. Okay? Does water have dipole-dipole forces? Yes. Does water have hydrogen bonding? Yes, it's got an HO bond, right? So it has hydrogen bonding. In fact, it has 2 hydrogen bonds. So I'm going to put it times 2. Okay? Nitrogen has London dispersion forces. Does it have dipole-dipole? No, why not? It's not polar. Everybody agree? Not polar? No polar bonds, okay? So no dipole-dipole. Does it have hydrogen bonding? No, because it can't, first of all, without even thinking, as soon as I said no to dipole-dipole, it's no to hydrogen bonding. But I don't have an HN bond. Okay? So, does water have more intermolecular forces than nitrogen? And therefore more intermolecular forces the higher the boiling point. Do you see that? So the question was, explain why water's boiling point is so much higher than nitrogen. Well, water has London dispersion forces, dipole-dipole, and 2 hydrogen bonds. Nitrogen only has London dispersion forces. The more intermolecular forces, the higher the boiling point. See that fully worked out answer. Okay? Or sometimes they don't give you the boiling points, they just say, rank these in order, in increasing boiling point order. Okay? So for example, let's go with methane and methanol and water. Okay, I'm not going to do, I'll just write water again because we've just done that. We've decided it has London dispersion forces. We decided it had dipole-dipole, and we decided it had 2 hydrogen bonds. Right? Now let's look at methanol. Does it have London dispersion forces? Yeah. Yep, because they all do. Does it have dipole-dipole? Yeah. Yes, it's going to be polar, right? Does it have hydrogen bonding? Yeah. Yes. Where? How many?
4.
Wrong. 1. Here. That's the only hydrogen bonding. It's an OH bond. OH. CH, is CH on our list? CH isn't on our list, so it's not an uber polar bond. Therefore, it doesn't have hydrogen bonding. But for the CH, pardon me. But it does for the OH. Everybody hear that? Okay. Methane. London dispersion forces?
Yeah.
Dipole-dipole? No, because?
It's not polar.
How do you know it's not polar right away? Fast. Because carbon and hydrogen only. Remember, repeat after me. Yeah. Carbon and hydrogen only is non-polar. Okay? So non-polar, so does it have dipole-dipole? No. Does it have hydrogen bonding? No, because definitely not. If I put an X beside dipole-dipole, it's not going to have hydrogen bonding. Okay? So carbon and hydrogen only, non-polar. Always. Okay, so besides, this is methane, which is natural gas, which is a fossil fuel, like crude oil. Oil and water don't mix, non-polar. Okay, so can you see the order in which the boiling points will be then? The more intermolecular forces, the higher the boiling point. So which of these will have the highest boiling point?
4.
The one with the 4. So this will have the highest. This will be the first or the highest boiling point. Then, second highest, the middle one, and the lowest or the third highest would be this one. And this is why this is a gas at room temperature. Only one force to stick them together, so actually they're quite far apart at room temperature. Whereas these guys are liquids at room temperature, and therefore they're able to stick together a little bit more. Does that make sense? Okay. This boils at 100, this boils at something like 35 degrees Celsius. So on a hot day, this would be a gas. A hot day in Phoenix, anyway. Not a hot day here, really. Who wants to go to Phoenix? Yeah, okay, let's go. All right. Does that make sense, you guys? Okay, so when you're asked to explain anything about boiling points or intermolecular forces, you make this list. Everybody okay with that? Sometimes, and paying attention to the 2 hydrogen bonds, because that's also part of our list, 4 and then 3. Okay, but sometimes there's a tie. For example, let's take methane, and let's take octane. Do you know where you find octane? 5, 6, 7, 8. Do you know where you find octane? In gasoline. So what state is it at room temperature? Gasoline you put in your car.
Liquid.
Liquid. So this is liquid. What's that? Methane that comes out of your stoves to heat your stoves. Gas. Okay? Does octane have London dispersion forces?
Yep.
Does it have dipole-dipole forces? No, because only carbon and hydrogen, non-polar, therefore no dipole-dipole. And does it have hydrogen bonding? No, because there's no OH bond, NH bond, or FH bond. And because as soon as I said no to this, I have to say no to this. Okay, so do you see if we have a tie here?
Yeah.
Okay, and you're still supposed to rank them. Highest, second highest. Okay, now is this third or fourth, or is this third or fourth? Okay, so when you've got this kind of a tie, and it only happens with London dispersion forces, the first thing you look at is the number of electrons. Because remember what London dispersion forces are? They're supposed to be the electrons in one molecule being attracted to the protons in the other, and the protons being attracted to the electrons in the other, right? So the more electrons and the more protons, the more London dispersion forces. You see that? So only when I have a tie, I then start thinking about electrons. Which molecule will have more electrons? This one, because it has more compounds. And in fact, I could count them if I wanted. Do you remember in Science 10? How many electrons does hydrogen have? 1 valence electron, right? And in the first ring, only 1 electron. So I could go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18 electrons. How many electrons in carbon? Well, there are 6 protons, so therefore there must be 6 electrons. 2, 4, right? So then 6 and 6 and 6 and 6 and 6. And I could add all that up and I could count how many electrons there are. Make sense? So this has more electrons, so therefore it has more London dispersion forces. So it'll have a higher boiling point than this guy. So this guy is now third, and this guy's now fourth. Which makes sense because this is a liquid, like these are liquids, so that should be with this. So it all kind of gels together for us. Crystal clear or clear as mud? Okay. In your packages, I've set a snap booklet page. What have I said? 77 and 78. So we're going to do snap book page 77 and 78. And then there is a question sheet at the very back of the package too, so we're going to do both of those. Okay, so snap 77 and 78 is where we will start though, trying to piece this all together. Okie dokie?